So Jacob Lurie is giving from the Institute for Advanced Science. He's giving the Felix Klein lectures as part of the Hausdorff trimester program. Really, but here at MPI. So ahead.
All right, thank you very much. Thank you for having me here. It's a pleasure to be given an excuse to come back to Bonn. What I would like to do eventually in these lectures is tell you something about some joint work with Bhargav Bhatt on what you might call the Riemann-Hilbert problem in non-Archimedean geometry. But in this first lecture, I'd just like to set the stage by talking about the Riemann-Hilbert problem in its classical context over the complex numbers. So okay, so the story starts with Hilbert, who gave a very famous address in 1900, laying out a series of 23 problems for the mathematicians of the 20th century. And in particular, I want to talk about the 21st of those problems. So here's some of the original text. My German is not so good, and my clicker is not so good either. Maybe if you could fix. Okay, so Hilbert asked, oh, it works for you.
Yeah, it works for me. Perhaps just a little bit of conviction in the press.
Huh. Okay, so Hilbert asked if there always exists a linear differential equation of the Fuchsian class having given singular points and monodromic group. So I'm going to tell you what that means in just a moment, but some question about Fuchsian differential equations. Hilbert thought that it was important, so what's the status? A few years after he asked it, someone gave an answer in the affirmative. And much more recently, there's been an answer in the negative. So this is an odd state of affairs in mathematics, but I think it's fair to say I only showed you the beginning of the text of Hilbert's address, but even if I had given you the entirety of what Hilbert said, it's not completely unambiguous what he was asking, and depending on how you interpret it, you can get different answers to this question. Okay, so let me explain at least one interpretation of it. So we're interested in holomorphic functions of one complex variable z, and we're interested in giving a system of differential equations. Let's say you have for n functions, f1 through fn, and the differential equations say that the derivative of each fi is some linear combination of the other functions fj. And the coefficients which appear in that linear combination, they're not constants, they're also functions of z. And you say this is a Fuchsian system if there's functions of z of a specific type. So you allow these functions to have singularities at finitely many points, a1 through ak, but you require that they have at most simple poles at those points, a1 through ak. And moreover, you require that these functions aij are rational functions of z that vanish at infinity. So concretely, what that means is that each aij is something that you can write as a polynomial function of z divided by z minus a1 through z minus ak, where the degree of that polynomial is required to be less than k. So what's an example? So for simplicity, let's say we just have a single equation, single function f, and we have a singularity at 0. So here's an example. I could demand that the derivative of f is f divided by 2z. So this is an equation that we hopefully all know how to solve. Solution is f of z is the square root of z. But probably we also all know that that's not completely unambiguous. So first, there's some funny business at the point where you have a singularity, namely the point 0. But for every other value of z, there's not one square root, but 2 that differ by a sign. And as a result, this function f of z equals square root of z, it's something that you can define locally on any simply connected region of the complex plane that avoids zero, but it's not something that you can define globally. So for example, if you decided that you wanted to set the square root of 1 to be 1, that defines for you what this function should be at the point 1 and in a small neighborhood of 1. And then you can try to analytically continue that to the entire complex plane. And you'll find that that analytic continuation procedure, it doesn't quite work, because as you travel around the origin a full 360 degrees, you'll discover that you want to declare that the square root of 1 is -1 at the other end. So this is actually a general phenomenon. So let's say I give you a Fuchsian system of differential equations with singularities at these points A1 through AK. Well, if you fix a point which is not one of these points of singularity, then you can find a system of solutions to these differential equations in a small neighborhood of that point. In fact, if you look at the collection of all solutions, they'll form a complex vector space of dimension n. Namely, you can prescribe the values of f1 through fn at any point x that you've chosen. And that lets you find a system of solutions in a neighborhood of x, but there's some obstruction to finding these globally on the entire complex plane minus k points. You'll find that as you try to analytically continue them, you encounter some difficulty as you travel around each singular point. And this difficulty can be encoded by a group homomorphism from the fundamental group of this punctured complex plane into the group of invertible n by n matrices. So this representation is called the Monodromy Representation. And let's just give an example, slightly generalizing our previous example. Let's say, again, we have only one function, and we have a singularity only at the origin. So the most general Fuchsian system of this type is something that says the derivative of f is alpha times f divided by z. And well, you know how to solve this. The solution is z to the alpha. Now, if alpha is an integer, that's a well-defined holomorphic function on the entire complex plane minus 0. But if alpha is not an integer, it's something that you can define as a holomorphic function locally near every non-zero point, but there's some obstruction to defining it globally. That obstruction is measured by this monodromy representation of what happens as you travel around the origin. So in this case, the fundamental group is just the group of integers. And a generator goes to an element of GL1C, meaning an invertible complex number. And it's not hard to figure out what this complex number is. It's as you travel around the origin, this function picks up a factor of e to the 2 pi I alpha. Okay, so this is a construction that you can do in general. Given a Fuchsian system of differential equations, you can extract this monodromy representation. And Hilbert's question is about whether or not every representation can come about in this way. So a representation here is a very concrete datum, namely the fundamental group of the complex numbers minus k points is a free group on k generators. It's freely generated by k loops that just essentially go around each of the points that you've removed. And so giving a representation like this is just giving a k tuple of invertible n by n matrices. And so roughly the dimension of this parametrizing data of this kind is k times n squared. And that's the same number of parameters that you need to specify a Fuchsian differential equation with singularities at the points A1 through AK. So you can ask, it seems reasonable that maybe every representation can come about in this way. So this is called the Riemann-Hilbert problem. So given a representation, produce the differential equation that has that monodromy, as it has that monodromy representation. So it's named after Hilbert because Hilbert made this one of his 23 problems. And Riemann, I believe, got his name attached because Hilbert suggested that Riemann might have been thinking about this. So I Felix Klein was a contemporary of Hilbert. And so since these are the Felix Klein lectures, I thought I would look up if he had said anything about this. And he wrote a treatise on the mathematics of the 19th century in which he said this: Riemann speaks in such a careless way, as if the existence of functions having the given singularities in monodromy is self-evident, and one only has to study their properties. So that sounds a little harsh. We can interpret this in the most general way as saying that Klein thought that to Riemann, this would just be obvious. It would be so obvious that you could do this that you didn't even need to give a proof. So what I would like to do now is just tell you a way that you might think about this problem from a more modern vantage point where that would maybe be justified. So how can you think about this? Well, let X be the Riemann sphere. So complex numbers, union the point at infinity. And let me write E for the trivial vector bundle of rank n on X. And then giving a system of differential equations, you can think of as giving a connection on this trivial bundle E. And the dictionary is such that giving a system of solutions to the equation is equivalent to giving a flat section of this vector bundle E. That is a holomorphic section of E that is annihilated by this connection nabla. And well, the Fuchsian condition translates naturally into this language as saying that this connection is meromorphic with, at worst, simple poles at the points A1 through AK that you designate as your singular points, together with the point at infinity. And so as long as you stay away from those points, the vector bundle E can be, or near any point which is not a singular point, you can find a basis of sections for E which are flat with respect to this connection. And the flat sections determine a local system on this punctured complex plane. And Hilbert's question in these terms is, can you get every local system out of this construction? And when you say it this way, there's nothing special about the Riemann sphere. You could ask this for any Riemann surface at all. So let X be a Riemann surface. And let's say U is an open subset, which is obtained by removing finitely many points. And let's say we're interested in representations of the fundamental group of U on a finite dimensional complex vector space. So these are the same thing as local systems on U. That's more or less a definition. And by some elementary differential geometry, the datum of a local system on U is equivalent to the datum of a holomorphic vector bundle equipped with a connection. The local system can be extracted by looking at sections that are flat with respect to that connection. And so the representation of pi1 of U, it gives you a vector bundle with connection, but only on U. You could ask, though, could you extend this to a holomorphic vector bundle on the entire Riemann surface X, such that maybe the connection doesn't extend in a holomorphic way, but it extends in a way where it has, at worst, simple poles at these finitely many points that you've removed. And when you phrase the question this way, it's not hard to see that the answer is yes. So the problem is local on X. You just need to solve it in a small neighborhood of every one of those points that you've removed separately. And therefore, you might as well assume that X is the unit disk in the complex plane, and that U is the open subset obtained by removing the origin. And in this case, well, the local system is determined by a very small amount of data. It's just a representation of the fundamental group of this punctured disk. So that's given by a single matrix, B. And now some elementary linear algebra will tell you that that matrix has a logarithm. You can write it as e to the 2 pi I a for some n by n matrix of complex numbers A. And then once you've chosen A, you can just write something down. So you take your vector bundle to be the trivial vector bundle of rank n, and you give it the connection where the connection matrix is A times dz over z. So this corresponds to the Fuchsian system of differential equations, where all of these coefficient functions are just some constant divided by z. This is just a many variable version of what we discussed a moment ago when we talked about Fuchsian systems having singularities only at 0. And an elementary calculation will tell you that when you study the monodromy representation of this particular system of equations, you just get e to the 2 pi I a, which is the monodromy that you wanted. Okay, so what's the upshot of this? Well, let's go back to the original context where we had the Riemann sphere and we removed finitely many complex numbers together with infinity. And so what we just said would tell you is that if you take any local system, you can think about it as a vector bundle with connection on U, and you can extend it to a vector bundle with connection on the Riemann sphere having at worst simple poles. And now if E was the trivial vector bundle, that would be a solution. This connection would be a system of a Fuchsian system, differential equations. And that would be a solution to the question that Hilbert asked. The thing to watch out for that I think went unnoticed for some time is that you can't always arrange that E is the trivial vector bundle. And there's explicit examples where E cannot be chosen to be trivial. But vector bundles on the Riemann sphere are not very complicated, right? They might not be globally trivial, but they're always trivial after you remove any point. So for example, they're trivial after you remove the point at infinity. So there's, although in some sense the answer to Hilbert's question is no, there are all kinds of slight tweaks you can make to the question that turn the answer into yes. For example, if you dropped the growth conditions on these rational functions aij, then the answer would become yes. And let me remark that I'm appealing to something here. So if you produce these connection by the procedure of the previous slide, by just solving some problem locally, what you a priori know about that connection is that the coefficients of the connection matrix are meromorphic functions on the complex plane that have simple poles at the points that you're interested in. Now, knowing that those correspond to rational functions is appealing to a theorem. It's a piece of 19th century mathematics that any meromorphic function on the entire complex plane is a rational function, but it's something that makes a connection between complex analytic geometry and algebraic geometry. Okay, so this is a story of Hilbert's problem. It's a story about local systems on the complex plane minus finitely many points, or more generally, local systems on a Riemann surface. But you could ask, what happens if you look at manifolds of higher dimension? So several of the things I said would just carry over immediately. So for example, let's take X to be a complex manifold. And let's assume for simplicity that it's connected. So then representations of its fundamental group are the same data as local systems on X. And again, by differential geometry, that's the same data as a holomorphic vector bundle on X equipped with a connection. The only difference from the one-dimensional case is that now you have to mention explicitly that it's a flat connection. In dimension 1, all connections are flat. So that's a completely general story. It doesn't really have anything to do with the question originally. But now let's pass to the world of algebraic geometry. So let me assume that X is a very special kind of complex manifold. Let me assume that it's a smooth projective variety over the complex numbers. It's something that's described inside of projective space as the solutions to a system of polynomial equations. So that principle that I mentioned earlier, that every globally defined meromorphic function is a rational function, has a sort of much more sophisticated 20th century incarnation which is called Serre's Gaga principle, or his Gaga theorem, which is that in this setting, if X is a projective algebraic variety, you can look at holomorphic vector bundles on X, just thinking of it as a complex manifold, or taking advantage of the algebraic structure, you can look at algebraic vector bundles on X. And when X is projective, there's no difference. Every holomorphic vector bundle admits a unique algebraic structure. And a consequence of this that you can deduce is that any connection on a holomorphic vector bundle is automatically compatible with its algebraic structure. That is, it comes from a connection that lives in the world of algebraic geometry. So let me mention a consequence of this, which is kind of amazing. So let's say that X and Y are smooth projective varieties over the complex numbers, and that they're isomorphic, not as complex varieties, but just as abstract schemes. So what does that mean? So X is something that's described inside of projective space as the solutions to a system of polynomial equations. The coefficients are complex numbers. Now, the field of complex numbers has a huge automorphism group. It has two automorphisms that are obvious, the identity and complex conjugation. It has lots of automorphisms that are not obvious. We only know about them because of the axiom of choice, and they're all incompatible with the topology of the complex numbers. But you can take one of these crazy automorphisms of the complex numbers and just apply it to all the coefficients that arise in the system of equations describing X, and you get a new system of equations which describes a new algebraic variety Y. Now, X and Y there's no reason that they should look the same when viewed as complex manifolds. In fact, they don't even have to be homeomorphic to each other. And Serre showed they don't even have to have the same fundamental group. But even though they can have different fundamental groups, the fundamental groups have the same representations. You can identify finite dimensional complex representations of pi1 of X with finite dimensional representations of pi1 of Y. And the reason is that these categories of representations have a purely algebraic description. A representation of pi1 of X can be thought of as a holomorphic vector bundle on X with a flat connection. But because of this Gaga theorem, that's the same data as an algebraic vector bundle on X with a flat connection. And that's something that can't see the difference between X and Y. Okay, so that's the story about projective varieties. What about varieties that are not projective? So let me still assume that X is smooth, so it's something that has an underlying complex manifold. But if X is not projective, then in general, this Gaga principle doesn't apply. There's holomorphic vector bundle on X might not have an algebraic structure. If it does have an algebraic structure, that algebraic structure need not be unique. But the situation is better if you want to talk about vector bundles that have a flat connection. So what can you do? So let's say X is a smooth variety and E is a holomorphic vector bundle on X, which is equipped with a flat connection. In other words, the data of a representation of the fundamental group of X. So first, let me assume that X is a quasi-projective variety, meaning that it embeds as an open subset of something projective that I'll denote by X bar. So that's some compactification of X. And now using Hironaka's resolution of singularities theorem, you can arrange that X bar is also pretty nice. So you can arrange that the compactification is also smooth, and moreover that the boundary, X bar minus X, is what's called a normal crossings divisor. So that means that you really understand exactly what the structure looks like at any point of the boundary. So using this, Deline showed that you could extend your holomorphic vector bundle E on X to a holomorphic vector bundle on the compactification where, well, the connection doesn't quite extend, but it extends as what's called a connection with logarithmic singularities. So this is the higher dimensional analog of saying that a system of differential equations is Fuchsian. And the argument that he used is more or less the argument that I showed you. You want to form this extension, you look locally in a neighborhood of any point that lies on the boundary. And in that case, a small neighborhood of that point is very simple, and the local system is described, well, before it was described by a single invertible matrix, now it's described by a tuple of commuting invertible matrices. And you perform some local construction. Now, once you've extended to the boundary, you're in the situation of the previous slide. You have a holomorphic vector bundle on a projective variety, and it has a unique algebraic structure by Serre's Gaga principle. And then you can restrict that to the to the algebraic variety X that you started with. And that gives you an algebraic structure on this vector bundle E. So if you put all of this together, you get the following theorem of Deligne. So let's let X be a smooth algebraic variety over the complex numbers. There's an equivalence of categories of local systems of complex vector spaces on X, in other words, representations of its fundamental group, with the category that has an algebraic description. Algebraic vector bundles on X, which are equipped with a flat connection, which is required to be regular. So this word regular, I won't define in this lecture, but it's closely related to this notion of Fuchsian singularities that we discussed earlier. And so the equivalence going from the top to the bottom is more or less the construction that I sketched for you on the previous slide. It's maybe requires you to be a little bit clever, but the construction going bottom to top is just something very, very obvious. Namely, if you have an algebraic vector bundle with a flat connection, then you can first form the associated holomorphic vector bundle, which I'll write with superscript E holomorphic. And then you can look at the flat sections to get a local system. And so what is this saying? Well, it's some higher dimensional version of this solution to some higher dimensional Riemann-Hilbert problem. Any local system or any representation of the fundamental group of X, you can get it to arise as the monodromy representation associated to some system of differential equations. And moreover, they can be algebraic differential equations, meaning that the coefficients that can appear will be rational functions on this variety X. So let me just give an example of how a local system that arises in algebraic geometry. So let's say I give you a map between smooth projective varieties from X to Y. And for every point of Y, you can look at the fiber of that map, which I'll denote as X sub Y. And inside of Y, you can look at the regular locus for this function F. So that's the collection of points of Y such that for every point lying in the fiber over Y, the differential of F is surjective. So that's an open subset of Y, and Sard's theorem tells you that it's always non-empty. Now, if you take any point that lies in the regular locus, that fiber X sub Y, it's a complex manifold. It's a smooth algebraic variety. It has an underlying complex manifold. And moreover, as the point Y varies, these complex manifolds kind of look alike. They're not necessarily isomorphic as complex manifolds, but they are diffeomorphic as smooth manifolds. And in particular, they have the same cohomology. So you can look at the construction that takes each point of U to, let's say, the nth cohomology group of the fiber. And as that point of U varies, these finite dimensional vector spaces give you a local system on U. And by what I said on the previous slide, this theorem of Deligne tells you that this corresponds to an algebraic vector bundle on U equipped with a flat connection. And this particular connection has a name. It's called the Gauss-Manin connection. And there's essentially an infinite amount of literature studying this construction. So, take your favorite map from X to Y, take your favorite degree in which you want to study cohomology, do this construction. It will produce for you some interesting system of differential equations on the regular locus of that map, and then you can study those differential equations and see what they look like. Okay, so this is a very general story, but now let's suppose that you're interested in this story because you really want to understand the cohomology of the variety X. And maybe you want to use Y as a tool for understanding it. Maybe you want to say, well, in order to understand the cohomology of X, I'll first understand Y, and I'll understand each fiber of this map, and I'll somehow put all that information together. So that's a strategy which is sensible. But to really carry it out, you don't want to restrict to the regular locus. You have to think about all the fibers of this map, because the fibers that are singular are maybe the fibers where the most interesting things are going to be going on. So you can take the fiber of this map over any point of Y. In general, it won't be a smooth manifold, but it will still be a reasonable topological space. It's the underlying topological space of a projective algebraic variety. And you can study the cohomology of that fiber. Now, that's some finite dimensional vector space over the complex numbers, but now it's something that really depends on the point you chose. Like that cohomology group can have different dimensions at different points. And so it doesn't form a local system. Local systems are the wrong language for studying the structure that you see here. What you get is not a local system, but instead a constructible sheaf. And that constructible sheaf has a standard name, but that's not important for what I'm telling you. I just want to raise the question. Let's suppose that you wanted to think about not just the regular locus, but you really wanted to understand the sheaf that was given by this construction. Can you somehow translate that into the language of algebraic differential equations? And this is a rhetorical question. I wouldn't ask it if the answer wasn't yes. So maybe I should say, how can you translate this into the language of algebraic differential equations? So this is the starting point for the theory of algebraic D-Modules. So let me remind you of what Deligne's theorem said. Algebraic vector bundles with a flat connection are the same thing as local systems on X. Now, algebraic vector bundles in the language of algebraic geometry, these are locally free modules over the sheaf of polynomial functions on X that I'll write as OX. And local systems on X can be described in a similar way. These are locally free modules over a different sheaf, namely the constant sheaf of complex vectors, the constant sheaf associated to the complex numbers on X. And so when you say it like this, it's natural to ask if there could be some version of this correspondence where you just drop the locally free assumption on both sides. So motivated by this, we introduce a definition. Now, an algebraic D-module is an OX module E, which is equipped with a flat connection. That's some map from E into one forms taking values in E. And E is no longer assumed to be a vector bundle. It's no longer assumed to be a locally free OX module. It's only assumed to be a quasi-coherent OX module. So this is a definition, and now you could ask, what could you do with an algebraic D-module? So let's first go back and ask, what can you do with a vector bundle having a flat connection? So let's say E is an algebraic vector bundle, in other words, a locally free OX module. Something that I appealed to earlier is that any algebraic vector bundle has an associated holomorphic vector bundle. And so in this language, that's just obtained by taking E, which is a module over the sheaf of polynomial functions, OX, and tensoring it with the sheaf of holomorphic functions, which I denote by OX holomorphic. And now if E is equipped with a connection in the world of algebraic geometry, then this holomorphic vector bundle is equipped with a connection in the world of complex analytic geometry. That is, I'll denote it by the same symbol nabla. It's something that takes holomorphic functions with values in E to holomorphic one forms with values in E. And then earlier I wrote E holomorphic superscript nabla to indicate the flat sections of that vector bundle with connection. In other words, the kernel of the map nabla from holomorphic functions with values in E to holomorphic one forms with values in E. So that kernel is being formed in the world of sheaves on this X viewed as a complex manifold. And I'm just spelling this out for you to emphasize that this definition makes perfect sense without the assumption that E is a vector bundle. We just used that it was an OX module to make sense of E holomorphic, and we used that it had a connection to make sense of the flat sections. So that's something that makes sense more generally in the context of algebraic D-modules. So how does this construction behave? Well, let's start with the algebraic vector bundle case. Well, something that we appealed to earlier is that when you look at the flat sections, it forms a local system having the same rank as the rank of the vector bundle that you started with. So that's really a theorem about differential equations. It's saying that if you think of this vector bundle with flat connection as giving you some system of differential equations to solve, you can find solutions, at least locally, having given values at any point. And so a more informal way of saying this is that the holomorphic vector bundle here has enough flat sections, meaning that any holomorphic section locally can be written as a holomorphic linear combination of flat sections. A more precise way of saying that is that if you take the flat sections, which is a sheaf of complex vector spaces, and tensor with the sheaf of holomorphic functions, then you get E back again. So this is a story about algebraic vector bundles with a flat connection, but you can perform the same constructions more generally for an algebraic D-module, but these statements A and B will both fail in general. So if you look at the flat sections, you might not get a local system, but that's what we wanted, right? My motivation for introducing algebraic D-modules was that you wanted to extend the dictionary between vector bundles with connection and local systems to sheaves that are not local systems. But another thing that can happen is that the flat sections of E, it could just be too small. Like you could get 0, in which case this is not an interesting construction. So as a remedy for B, let me talk about a slightly more elaborate construction. So let's again first talk about it in the vector bundle case. So let's say E is a vector bundle equipped with a connection nabla. Then nabla, it doesn't just give you a way of taking functions with values in E and making one forms with values in E. More generally, you can take an n form with values in E and use the connection to produce an n+1 form with values in E, some version of the de Rham differential. And if the connection is flat, then this de Rham differential will square to 0, and you'll actually produce a chain complex. This is called the holomorphic de Rham complex with values in E. And so this chain complex was sort of implicitly there in our earlier discussion, because the first differential which appears here is nabla itself. And that the kernel of that, by definition, is what we're calling flat sections of E. So that's the 0th cohomology of this holomorphic de Rham complex. And what about the rest? Well, it's not that interesting, actually. The cohomology groups will vanish for n greater than 0. And this is essentially the holomorphic version of the Poincare lemma. So this is a local statement, and therefore you might as well prove it when you're dealing with the trivial vector bundle with the obvious connection. And in that case, what I'm saying is that any closed holomorphic n form is locally the differential of a n-1 form. But I'm bringing this up because that's a story about vector bundles with a connection. And if you have an algebraic D-module, this vanishing of the higher cohomologies is not generally going to be true. And that's good, not bad. Because what I told you earlier on the previous slide is that if you just look at the 0th cohomology, if you just look at the flat sections, that doesn't necessarily capture very much information about E. But there's more information by looking at these higher cohomology groups. Or better yet, you look not at the individual cohomology groups, but you look at this entire de Rham complex. So this leads us to the main theorem in the subject. It's called the Riemann-Hilbert correspondence. So let X be a smooth algebraic variety over the complex numbers. And now you can look at this construction that takes an algebraic D-module E and produces this holomorphic de Rham complex. So that's a chain complex of sheaves. And you've sort of entered the world of homological algebra here. So it's natural to extend this to get actually a functor of derived categories, from the derived category of OX modules with connection to the derived category of sheaves of complex vector spaces. And the Riemann-Hilbert correspondence is the statement that if you add the appropriate adjectives on both sides, this functor is actually an equivalence of categories. So this was proved independently by Kashiwara and Mebkhout in the early 80s. The version that I'm talking about is actually a slightly easier statement called the algebraic Riemann-Hilbert correspondence, which I think is due to Bailenson and Bernstein. So let me say a few words about what these relevant adjectives are. So each of these decorations is imposing some condition on the cohomology groups of the complexes that you're considering. So the superscript B means that you're putting some bound on the number of cohomology groups that is allowed to appear. On the left-hand side, the superscript RH means that the cohomologies are required to be regular holonomic D-modules. So the word regular is it's some condition that you can think of as having to do with Fuchsian singularities in the original story. And this word holonomic is essentially a finiteness condition. It's automatically satisfied for vector bundles with a flat connection. And on the right-hand side, this subscript C means that you restrict your attention to complexes of sheaves that have constructible cohomologies. Okay, so anytime you have an equivalence of categories, that means you have a functor going in the opposite direction. So in this case, I'm going to denote that functor by RH. It's called the Riemann-Hilbert Functor. And that's because it implements the existence of this functor is saying something about the solution to a very sophisticated version of the original Riemann-Hilbert problem. So it takes as input constructible sheaves. So that's some topological kind of data about the underlying complex manifold of X. It has to do with representations of the fundamental group of X, but more generally the fundamental group of various subvarieties of X, things like that. And it produces output things that have to do with algebraic D-modules, things having to do with differential equations with polynomial coefficients. And one thing to emphasize about this is that the right-hand side, this category of regular holonomic D-modules, is something which is defined in a purely algebraic way. There's nothing special about the complex numbers as far as the right-hand side is concerned. You could replace the complex numbers by any other field of characteristic 0. So for example, you could replace it by a number field, and then maybe there's interesting arithmetic to be seen. On the other hand, the definition of the left-hand side, so there I wrote xn, meaning the underlying complex manifold of X. So that really has something to do with the usual topology on the complex numbers. You're thinking of X there as a topological, as a complex manifold, something that is a Hausdorff topological space when you go to study sheaves on it. So both that category and the functor that relates them is something non-algebraic. It's something that uses the topology of the complex numbers. But a question that you could ask, and that the rest of these lectures are going to be about, is what can you say if you replace the complex numbers not by an arbitrary field of characteristic 0, but you replace it with some other field that has a topology, something like the field of p-adic numbers with its p-adic topology. So if you make that replacement, again, the right-hand side has some purely algebraic definition, which makes perfect sense. But is there some relationship with some kind of topological sheaf theory that can go on the left-hand side? So let me just give a brief preview of what the other lectures are going to be about. So X is going to be some algebra geometric object, for example, an algebraic variety. And the general kind of thing that I want to ask is for something like this Riemann-Hilbert functor. So something that relates topological coefficient systems like constructible sheaves to something like D-modules, something that you can think of as quasi-coherent sheaves on X with extra structure. And so I'm going to sort of discuss a lot of different constructions that fit into this general paradigm. So we just talked about the classical Riemann-Hilbert correspondence, which takes place over the complex numbers. In the next lecture, I'll talk about algebraic geometry in characteristic P. In lecture 3, I'll talk about a version of this in the context of perfectoid geometry. In lecture 4, I'll talk about this when X is a scheme or a formal scheme over the ring of integers in a perfectoid field. And finally, in the last 2 lectures, I'll talk about what happens over fields of more arithmetic interest, like non-Archimedean local fields like QP. All right, that's all I have for today. Thank you very much.